Very good. Well, it's really my great pleasure. Are we on? All right. It's really my great pleasure to introduce Dr. Gavin Schmidt. He is indeed from the Goddard Institute of Space Studies in New York. He's done a lot of climate research, and he's here to talk about what's causing recent climate trends. Dr. Schmidt.
So I very rarely followed three governors and an administrator of an EPA, and I'm extremely impressed that there's anybody here at all. So thank you very much. What I'm going to talk about is why we understand what's happening to the climate. Like, what are the fingerprints of change that we can recognize, that we can attribute, and that we can then understand and use to predict going forward. Okay, so if you want to just start the video. So I'm going to try something different. There's a lot of information on this video, so we're just going to play it over and over and over again until we've explained everything, right? So just to set this up, on the side here we have maps, and these are from the top. This is right at the top of the stratosphere, mid-stratosphere, about 30 kilometers up. The lower stratosphere, about 15 to 20 kilometers. The surface, that's right at the ground level. And then the bottom one is ocean heat content. So that's how much energy is going into the ocean. And then the lines going across, that's just the progression over time of the mean changes in the stratosphere, in the lower stratosphere, at the surface, and in the ocean, and all the way at the end there in the Arctic sea ice. And what I want to show you is how we can tell the difference between different drivers of climate change. Now, we know that many things can change the climate. We have 4 billion years of history, and anything that could have happened pretty much has happened, right? We've had wobbles of the Earth's orbit, we've had asteroids, we've had movements of the continents, we've had solar variation, we've had carbon changes, we've had land surface changes. All of these things have happened in the past, right? So we have 1,000 different ideas of what could cause climate change. But each of those different things has a fingerprint, has a specific pattern of effects that we can actually draw out. And what I'm going to do with this animation is I'm going to help you pull out the things that are changing. Now, there's 4 different lines on the line graphs, and they're all a little bit different. So there are observations on the surface temperature. You can see the white observations going forward. We don't have as long a record of observations for the other things, but you'll see there's the observations for the ocean heat content, there's the observations for the stratosphere and the upper stratosphere, and then the sea ice. And then the 3 colored lines are different climate model experiments that we run, simulations. And what we've done is we've taken the natural things that are going on, things that would happen regardless of our existence. So that's the variations in the solar cycle. It's big volcanoes going off and affecting the climate. It's the slow change in the orbit of the Earth. Right, those are all natural things that have nothing to do with us, right? And they're in the green line. So this is what the model predicts would happen only in the event that natural things are changing. And then the red lines are all of the human effects. Air pollution, deforestation, rises in greenhouse gases, irrigation, deforestation. Did I mention that one? And those are all human effects. And then when you put them together, you get the best estimate, you hope, of what actually happened, because there are human and natural things happening at the same time. Now, let's look for some of those fingerprints. Let's start off at the top, right? The mid-stratosphere. Like you can see, there's a bit of a waviness to the stratospheric temperatures. That's the solar cycle. We can see the solar cycle having an impact in the stratosphere. And then every so often, you'll see a pulse of warming or cooling, right? So when you have a big volcano, that tends to warm the stratosphere. And there's a couple of big volcanoes. There was one in 1883, which you'll see now. Well, okay. Oh, there we go. Do you see that one? Boom. It gets very warm. And then there's another couple of ones, Mount Agung in 1963, El Chichon in 1982, and Mount Pinatubo in 1991. And then you'll see them in the stratosphere, you'll see these pulses, these bright red pulses. And at the surface, you'll see them cooling. Because what happens when there's a volcano is that there's stuff that gets in the stratosphere that absorbs heat, that makes that warm, but underneath it's shielding the sun's radiation from the surface, and so at the surface it gets cold. So you have a pattern of behavior that's associated with those volcanic eruptions that's very short, right? So volcanic eruptions, very strong, warm, cool, very short. Solar variations, you see them, you can actually see them all the way down, but as you get to the surface, there's so much noise, it's very difficult to see them. So you can see them most clearly at the top, and they're all in phase. So when it warms everywhere, and when it cools everywhere. And then you see patterns of natural variability, things that the models just do on their own. You can see down here in the ocean heat content, these little blobs of heat kind of coming down around along the east coast of the US. Those are variations in the ocean overturning stream function. So this is the current in the North Atlantic that kind of comes down, brings a lot of heat to Europe, and those pulses are that current moving around and becoming a little bit stronger, a little bit weaker. You can see the variations in the ocean heat content in the tropical Pacific. Those are El Nino and La Nina events, right, that the models produce as a matter of course. And then there are the long-term trends, right? If you see what's happening, things are pretty flat. You know, we see these spikes. But then as you get towards the 1960s, where we are now in the 1990s, we see these large trends. We see these trends in the stratospheric cooling. We see these trends in the surface warming. We see the increase in the ocean heat content. We see the decrease in the Arctic ice. And when you look at this, and you look at the difference between the colors, that's where it really shows up. The green lines, the natural runs, they're flat, and then the ones with the anthropogenic forcings, they're going to match those trends. And when you look at that and you look at it together, that's the blue lines, you can see that the blue line trends match both the trends and the wiggles that we actually see in the real world. And you think about what's going on. The fingerprint of greenhouse gas warming is that you get cooling in the stratosphere for slightly esoteric reasons, but reasons that were actually predicted by Suki Manabe, who just won the Nobel Prize for Physics, back in 1967, before we had any measurements of temperature in the stratosphere. And that was a prediction that happened right now, almost over 40 years ago. And you can see that prediction coming true. And the greenhouse gases are warming the surface, they're cooling the stratosphere, they're increasing the heat content of the ocean, because the way that greenhouse gases affect the climate is that they make it harder for radiation to get out to space. So that means that there's more energy coming into the system than going out. That energy has to go somewhere, it's mostly going into the ocean, and so you can see that increase in ocean heat content happening at the same time that the surface temperature is increasing, that the stratosphere is cooling, and the sea ice is melting. And that combination of features is unique. None of the other forcings has that combination of features at that magnitude. And so when we go back and we say, what caused the recent trends? The answer is, it's us. Not a little bit of it, not a little bit of this and a little bit of that. All of the trends that you're seeing are at like the 7 sigma level ours. And that's very sobering, because that means that we are actually in control of these trends going forward. And that attribution statement, that attribution process that very clearly tells us why things have changed up until now, gives us a huge amount of scientific confidence that this is how things are going to be changing in the future. And it puts us, scientists, in a very odd position, because we spend our entire professional lives trying to find things from the universe, trying to understand what those things are, trying to make predictions about what that means, and then we're supposed to feel good that our predictions are coming true, that we have managed to get information from the universe and use it to make predictions. And as a scientist, you go, yes, what I'm predicting happened. How clever am I? But then when you see this intersecting with the real world and you see the impacts that that these changes are having, you find yourself in this very odd position of not wanting your scientific predictions to be true because you're not a sociopath. And so we have these two conflicting things. I am so proud of the work that goes into creating these models, developing these models, making these attributions, making these predictions, seeing these predictions go through. This on its own is a massive testament to our ability to understand the climate. But it's also a damning indictment of our ability to affect the climate. And climate scientists have found themselves in this very odd position of predicting things that they don't want to be true. And when people say, oh, you're just being alarmist, you're just doing this, we don't want our predictions to be true. And yet they are, and they have been, and they will continue to be. And NASA is working both on the modeling and on the observations, and we're tracking this, and we're tracking the causes, and we're trying to see how we can help make these predictions not be truer in the future. So thank you very much. Yeah, sure, as long as we have time.
Despite your discomfort with being so spot on with your projections.
Sorry, could I get a thing? I can't hear a word. Sorry. Yeah.
Despite your discomfort at being so spot on with your projections, what can you tell us as a scientist about how best you find to convince people who still don't accept the science at this point? What do we tell them beyond look at what you did?
So what do you tell people that don't see the science? Well, it's so clear now, right? 30 years ago, there was good faith arguments about what this meant. Were we getting the natural variability right? Did we have long enough records? Did we really trust this? Like that, 30 years ago, that was the case. Now, that's not the case. The signal is so far out of the noise that if you're not seeing it, it's because you don't want to see it. And that means that when you're talking to somebody, putting it in their face doesn't help because they're not looking, they're not listening. And there are other reasons for that. And so having deeper conversations with people that isn't about, look at the data, look at the science, right, is but what is going on? And that's been moderately successful in some cases, right? So you can go, okay, but why do you think this? Let's go back. What is it that you're really unclear? What is it that you're really worried about? And what you often find is that there's something else entirely that is preventing them from understanding what's going on, right? Or they may actually understand very well, but they don't want to admit it for other reasons. And you're much better off having a conversation about values, about attitudes, about things that they care about, and then kind of sneak this back in rather than kind of just throw more science at them. Because there's always reasons. People can always find reasons to argue, and a lot of the time, arguing at that level is basically a waste of time. There's 70% of the population in the US understands this now. They have questions, right? I have a uncle-in-law, and he says, well, but what about the sun? And I say, well, you know what? I just wrote a paper about that. And here, and doesn't this do that? And you say, yeah, hasn't climate always changed? Yes, it has. So I can be, you can be, not quite supportive is not the right word. I don't have to be confrontational to talk about these things. I mean, sometimes people really are confrontational, and it's usually a waste of your time to talk to those people. There are a lot of people who have genuine questions that are much more worthwhile to talk to than the 5% rump who are never going to come around.
we're going to wrap.
Okay, thank you.
Thank you, Mark Heaton from the state of New Mexico. I had a question regarding the data. Is that posted somewhere similar to what, let's say, a doomsday clock would be to give us this sense of urgency and continue with momentum?
I mean, all of this data is publicly available, right? So this is, if you want to look this up, you can and send it to your friends. This is SVS, which is the Science Visualization Studio at Goddard. And it's an animation called Climate Drivers. And on that page, there's links to all of that data. Now, putting it into a doomsday clock, I don't know quite what that would look like. I mean, if you have thoughts, then, you know, we have great folks at the climate.nasa.gov website. We're always looking for new ways to show off our understanding, the data, and what that means. And so if you have ideas for that, feel free to drop me a line, and we could discuss, you know, kind of new initiatives on that. Okay, thank you very much.